Hello and welcome to the Temperature Sensor Calibration IAR Embedded Workbench IDE Sensor Lab Code Explanation and Project Demonstration video. In this short video, I will be going over the code within the IDE used and the board design in order to go and measure temperatures in a room or in contact with this temperature sensor to the left on the board, the breadboard right there. And right now this board is displaying the temperature in degrees Celsius, and these are some calculations I did for error and some values that I calculated for the room temperature, the resistance value that I actually had, and the difference between my voltage reference on the board, which you can see says 3.3 right here, but I measured that to make sure because it changes depending upon not every board is the same, and also I wanted to make sure what it actually is, and the loading effect can affect the actual voltage sum of the circuit it's connected to. Anyway, so we also have an explanation of the overall project. That will be that this project measures temperature using a MSP430 NTC Thermistor connected to a MSP430 microcontroller. The Thermistor is wired in a voltage divider circuit with a fixed 9.87 kilo ohm resistor. You try to get a 10 k ohm, but mine was slightly off, so I accounted for that in the error calculations. One end of the resistors is tied to the 3.3 voltage supply on the board, and the other end connects to the thermistor. And the midpoint between them is connected to the MSP430's ADC, which is analog to digital converter input on pin P1.3. As temperature changes, the thermistor's resistance changes, which causes the divider voltage to rise or fall. This changing voltage is the electrical signal to the microcontroller that the microcontroller uses to determine temperature. The code itself is written in C and compiled using the IAR Embedded Workbench IDE for MSP430. The program configures the ADC to read channel A3, sets up timer A to trigger once per second, initialize the LCD controller so the temperature can be displayed on the 6-digit segmented LCD screen. Every second the timer interrupt starts a new ADC conversion. The ADC converts the analog divider voltage into a 12-bit digital value inside the ADC interrupt. The program converts this digital value back to the actual voltage using the known ADC step size. From that, the code calculates the thermistor's resistance using the voltage divider formula, and once the resistance is known, the program applies the beta form of the Steinhart equation. This produces the temperature in Kelvin, which is then converted to Celsius. The temperature is split into integer and fractional digits. Each digit is written to the LCD segmented memory, so the temperature appears on the display. This entire process repeats once per second, creating a continuous real-time temperature reading. In addition to the basic operation, it took some measures, like I said before, some accuracy of the measurement depends on 3 important error sources, which was the R naught error, the T naught error, and the V reference error, which So I took those values down and recorded them for you here, and you could see they are 1.3% for the R naught error, 12.4 for the T naught error, and V reference is less than 1% for those errors. And that's a resistance error, temperature error, and voltage reference errors. And that's how you do the calculation using that formula. Basically, the R naught error comes from the fact that thermoresistor's nominal resistance at the reference temperature, usually 10K at 25 degrees Celsius, is not exact. There's also manufacturing tolerances, which can mean that the real R naught may be slightly higher or lower, because the Steinhart equation uses the ratio R divided by R naught. Any error in R naught directly shifts the calculated temperature. A thermorestor with a 1% or 5% tolerance will introduce a corresponding temperature offset. T naught error comes from the uncertainty in the reference temperature using the equation. The beta formula assumes that R naught is measured exactly at 25 degrees Celsius or 296.15 Kelvin. If the real calibration temperature differs from this assumed T naught, the computed temperature will be slightly off. So that's why even a small error in T naught propagates through the logarithmic term and causes a temperature shift across the entire measurement range. The V reference error comes from the ADC's reference voltage. The code assumes the ADC reference is exactly 3.3, but in reality, the supply voltage may vary with load, as I mentioned before, battery level, or a regulator tolerance. Since the ADC converts voltage into a digital number based on V reference, any deviation in V reference changes the calculated sensor voltage. This leads to an incorrect resistance calculation and therefore an incorrect temperature. Even a few percentage of V reference variation can noticeably affect the reading. So that about summarizes everything here. The circuit and the code worked correctly after debugging a few errors in it. And looking at the warnings, which was just one for because one of the part of the code was referenced, but it wasn't used in the actual code, but it had a line for one of the temperature conversions, but it wasn't like used. It was just kind of like a warning on it, but it happened to do with something that it wasn't actually used in our code, but it was there so that it could be used, and you could call it if you needed to. If you could go and add a line of code to turn it on if you wanted to. So that is it. And one thing to always remember is always include these unavoidable real-world deviations, because in some contexts they can be life and death, and in others they can just be the difference between having a good day and a bad day. And thank you once again for joining me on this short video, and hope you enjoyed.